So, as I said, this is just some slide to show that credit goes up and down for reasons that are not well understood. Oops, now I need to be able to advance the slides. Okay, all right. So credit cycles are driven by something called leverage, and meaning we're still hearing an echo over there.
Okay. Do I do that?
Sorry. Okay. So credit cycles are driven by something called leverage. So what is leverage? Leverage is when you buy assets with borrowed money. Buying assets with borrowed money sounds crazy. It is a little crazy, but probably a large number of you have done it in a big way. When you buy a house, you normally go get a loan from the bank. You buy the asset, and the asset is the collateral for the loan. So this is something we do all the time, but we do it more or less at different times. And one of the things we see is when credit shuts down, the economy shuts down. So we really do rely on credit in a regular way. There's a sort of narrative theory by Minsky about what causes this. And so I've said leverage goes up due to competition for returns. As the leverage goes up, meaning people are borrowing more and more money to get the assets, negative shocks are amplified by the leverage, and that triggers a crash. So it's kind of a story he told, no math. And then my good friend and close colleague, John Giannakopoulos, made a theory of leverage in a traditional economics kind of way, assumed there's heterogeneous investors, that optimists tend to use more leverage, that bad news gets amplified, the ownership goes from the optimist to the pessimist, and then you get a crash. But it's a very qualitative theory. Now I'm going to present you a more dynamical theory, very simple theory. Key fact with passive investors. So if the leverage is greater than 1, if you are buying asset, like let's suppose you're buying a stock using leverage. How do you do that? You go borrow money from a prime broker. They give you this money, you buy the stock, but you're always conscious that you owe them money, right? Now, if the price of the asset goes down for some other reason, then your asset's worth less. And a typical prime broker is going to give you a leverage target. They're going to say, your leverage can't go above this amount. So if your leverage goes above that amount, what do? You sell the asset. And when you sell the asset, you're selling typically into a falling market because you're selling because the price of the asset went down. So now you're selling causes market impact and amplifies price going down. So that's the underlying reason for most crashes, that people end up selling into falling markets. So, all right. Now, I'm going to give you a model for how this can happen, even when investors are all behaving very prudently. You know, you go back to 2008. Why did we have the 2008 crisis? A lot of people will say, well, it's those greedy bankers. Yes, that's true. But it wasn't because they were cheating in general. I mean, a few of them probably were. It was because they were being too aggressive, but actually I'll show they were being too aggressive, but also they were following prudent risk management, but they didn't understand the emergent phenomenon side of the equation. That is, they didn't understand the systemic risk that was created by the risk management policy. Now, how did we arrive at this model? My student, Christoph Eimans, and I were building an agent-based model of interacting banks. So, you know, we were just kind of playing around. We had several banks. The banks would lend money to businesses. If the business didn't pay them back, one of the banks might default. So we were kind of thinking about those kind of things. But the slide on top here shows what the price was doing when we were just kind of running the banks and running the economy. We had a little economy, little virtual economy. And this is the price going along through time. and we said, okay, let's impose risk management on the banks. Now, risk management at the time was, there was a standard protocol called Basel II. We've moved over to Basel III now, by and large. But under Basel II, I'll explain more what that is in a minute. But we imposed Basel II, and when we imposed Basel II on our virtual economy, it started doing this. So we said, wait a minute, there's something screwy going on here. And so at first we thought maybe there's some bugs, so no bugs. And then we began stripping down the economy. We said, well, let's figure out why this is happening. We kept pulling things out of the economy. We knocked it down to one bank. We then got rid of the real economy. That is the part that actually produces stuff. And it kept happening. And we actually made things so simple. We got it down actually to a two-dimensional dynamical system. I'll say more about this in a minute. But then we made a model that we thought was more realistic. So let me show you the story. And as we polished up our story, the story began, let's explain what happened here in the run-up to the great financial crisis and what caused that crisis to happen. And we argue that, well, there's a lot of details, there's a fairly simple mechanism. Now, what this slide here shows is US broker-dealer leverage. Everything is normalized on some scale. These three time series all start at 1, just to make them comparable. And so the dashed blue line is what the stock market did from roughly 2003 to the end of 2015. The dashed rust-colored line is volatility. That is how much are markets bouncing up and down. So what you can see is during this period, the great moderation, it's sometimes called, or it used to be called, before that became embarrassing. In the run-up to the crisis, there's a nice smooth rise in prices, and there's a drop in volatility. It's as if, the sailing was getting very smooth, everybody was very happy, or at least the investors were very happy. This black line shows leverage. So what you see is more and more borrowing was going on. And then shortly before the crisis, there was a big spike, and then it fell, the market crashed, and volatility spiked up. So we wanted to see if we could make a simple model inspired by this behavior that we were seeing to explain that. Or really what happened is we figured out how to explain this, and we realized this made a good story to apply it to. Now, how does the model work? We have two agents in the model, a bank and a fundamentalist. And we have one risky asset plus cash. So think of that risky asset in the previous picture as the entire stock market. This is what an economist would call a representative agent model. So we know in the real economy, there were many investment banks and many investors and so on. Let's just bring it down to two investors to see how it works. So one of those is an investment bank like Lehman Brothers, and the other one is a fundamentalist like Warren Buffett. So the fundamentalist buys undervalued assets, doesn't use leverage, carefully tries to figure out what things are really worth and buy stuff that's worth, so they believe are worth something. Whereas the investment bank is doing a lot of stuff, but they have, in this case, they're just either they're in cash or they're in the asset, but they're using leverage, right? Now, so then we make 4 assumptions. First assumption is that the bank uses an exponential moving average of historical volatility to estimate expected volatility. So this is something everybody does in financial markets. Volatility is fairly predictable. It's strongly autocorrelated. You can make use of that autocorrelation to predict it. There was a Nobel Prize to Rob Engel in the 80s for coming up with a model that predicted volatility. The other assumption we make is that both investors use Basel II risk management. I'll explain that in a moment. So they use something called value at risk together with the exponential moving average of historical volatility to set their leverage targets. So they're adjusting their leverage based on how much risk they think there's going to be. If they think there's going to be more risk, that is higher volatility, they lower their leverage. And if they think there's going to be lower volatility, they raise their leverage. Very sensible thing to do. Please stop me at any point and ask questions if I'm not being clear. The third assumption we make is that price formation, we assume supply equals demand, and that, so basically we have our two investors. They both are stating how much of the asset they would like to hold. So they have supply and demand functions, or excess supply, excess demand functions. And we assume that the price is set at the point where their functions cross. And finally, as I said, we assume we have a fundamentalist who buys the undervalued asset and sells the overvalued asset. If the asset's overvalued, they'll want to get rid of it. If the asset's undervalued, they'll want to hold more because they believe if it's undervalued, it's going to go up in the future. So is the model clear to everybody? Yes?
Basis belief of the true value.
Yeah, so here we're just assuming God is telling the fundamentalists, okay? So the fundamentalist is getting some decision that's a random walk. So the values of the assets going up and down. Good question. Okay, now, okay, so this is just explaining more about leverage targeting. So if the investment bank has a leverage target, if the current leverage is too low, they borrow some more money and buy more of the asset. If it's too high, they sell the asset and pay back some of their loan. So that's what the bank is doing in this model, and that's what they do in reality. My friend John, well, maybe I shouldn't go into the story. John was inspired to do the model that partly inspired this by the fact that he was effectively the chief scientist for a hedge fund that's a leading trader of mortgage-backed securities. And they had a margin call by their bank in 1998 where the bank told them in one day you have to pay back your entire loan. And their company nearly went under as a result of this. You can see the movie Margin Call with Kevin Spacey. It was somewhat like in the movie, except they weren't doing dodgy things. And so he said, wow. And then he wrote down this model for leverage. So this is where one of the ideas comes from. So now the way Basel II works is that leverage is what you want to set. You make an estimate of volatility. If the volatility is high, you lower the leverage. If the volatility is low, you raise the leverage. So this is the equation that Basel II, which was the agreement that people were following at the time, would have you follow. So the bank's just going along, estimates volatility, adjusts leverage accordingly. And it's a very sensible thing to do. If everybody else is doing something different and you're the only one doing it. But now we have a world where it's a representative agent. So effectively, we're assuming everybody's doing it. Okay? Yep.
And should I think about setting a leverage target and setting a risk target? How risky you want to play the game?
Yeah. But here what you're saying is you've decided how risky you want to play the game. And so you're adjusting your leverage target to maintain a constant risk, right? A more aggressive investor would consistently take higher risks, a less aggressive investor lower risks. And that will be a parameter in the model. And we'll see what happens as we adjust the aggressiveness of the investor. That's actually this parameter alpha right here, okay? Which you can set constant or you could perhaps change it through time. Okay, so this is the diagram of the model just to reinforce how it works. We've got the fund, that's Warren Buffett. We've got the bank, that's Lehman Brothers. And so Warren Buffett, he shocks are hitting all the time. He goes, oh, the asset's now worth more or less. If the asset becomes worth less, he says, I want to buy some. And so he detects the mispricing, updates his portfolio weight. Then we update the asset price. Simultaneously, the bank is updating the risk estimate, enforcing the leverage constraint, and we're adjusting the asset price. Okay, and this is what the resulting model looks like. You can see it's a dynamical system, iterated dynamical system. So depending on all these quantities and its sort of complicated. I don't want to drag you through the details of this model because you'd have to understand what all these definitions are and so on. But it's just doing what I told you. I just wanted to give you the gestalt of it. It's a little complicated, not too complicated. We actually initially, when we were stripping everything down, we stripped it all the way down to a map that was just two-dimensional. But that was not as economically plausible. We got similar behavior, but not as rich and not as plausible. All right, so how does this model work? Well, so we have some parameters. One of the parameters is the size of the banking sector versus the fund. That is, you can decide at the beginning who gets the money, right? If the initial condition is Warren Buffett has all the money and the investment bank is tiny, that's different from the investment bank has lots of money and Warren Buffett doesn't have as much, right? So that's an adjustable knob. It turns out it's pretty similar to adjusting that risk parameter. We can take the bank, even if the bank is smaller, if the bank's really aggressive, that's also going to cause things to change. So you'll notice the x-axis in this is actually in years. One of the nice things about this model is we can take these equations I showed you a minute ago and put in, basic quantities a priori, like, well, how are we computing the value, the leverage? We could put in some parameter based on what we knew people did, more or less. We could look at the exponential moving average. Well, it turns out most people in the market use around a 2-year time scale for their exponential moving average. So we put 2 years in there, and the model has units, so you can then we put in annual units, and so you see when the banking sector is small, things are dominated by the behavior of the value investor. Things are all pretty stable on the left. On the right, we make the banking sector bigger. When we make the banking sector bigger, notice now we see this sort of spiky behavior that I showed you before. So we saw the basic phenomenon, and now we had a simple model where we could really understand exactly what's going on. One of the striking things is when we actually turn the noise all the way off. You might think, well, then things should just settle to a fixed point, which they do if the banking sector is small. But if the banking sector is big, you see an oscillation. So you see this slow build up. It doesn't have quite the same shape as before. So you see this followed by a crash, slow build up followed by a crash. And it just does that indefinitely, although the intervals are not strictly periodic. And as you can already see, the heights of the maxima vary somewhat. So this is a picture of the chaotic attractor that you get when you do this. So here we see this is the ownership of the bank. How much of the asset does the bank own? This is the perceived risk of the bank. How volatile does the bank think the market is going to be? And then price is up there. So what you can see is it goes around this circuit. Up here is where the price is at its maximum. The bank has maximum ownership, maximum leverage, and then you see the crash. We're actually just making dots. When you see the dots distinctively, that means things are moving fast, and then it slowly builds up again. So it crashes like that, and then it climbs up and it crashes. And this is a Poincare section, meaning you effectively take a slice through the tractor. You look at every time it crosses through that plane, then you make a dot. So here we're just plotting perceived risk against ownership, and you see this sort of fractal structure that you expect to see from a chaotic attractor. And this happens even without any noisy inputs. And then you can make a bifurcation diagram, and you see that the system can be stable, or you can have leverage cycles on a chaotic attractor, or it can just be completely unstable and go up to infinity. That's something we don't want the financial markets to do. It's bad enough when they do this. One of the things you see is that it's a flip bifurcation, meaning, I think it's a flip bifurcation, anyway. When you cross from the stable region to the leverage cycle region, the cycle appears at full amplitude. So you just go boom from one domain to the other. Now, and so here's a comparison of the model against the data. I had my graduate students sort of fiddle around to make it look as similar as he could. You can see it matches up pretty well. It doesn't quite match up because we've got the, we don't really get the big leverage spike, but we more or less get the other things. Right. So what is this telling us? Let me just see, do I have another slide? No. What is this telling us? You know, okay, I've written several papers about the financial crisis of 2008. You all know it involved housing markets in the United States, mortgage-backed securities. Basic story is that this new invention, mortgage-backed securities, that allowed banks to distribute their risk for issuing mortgages because other people could own these assets. So effectively, lots of people could own mortgages. Lots of Europeans, it turns out, owned mortgages in the United States because it was considered a really cool investment because it just went up and just made money. And then what happened was it coincided also that this made the banks overconfident. So they began lending money on more and more generous terms. This was actually fueled by liberals in the United States who said wanted poor people to be able to own their own house. Seemed like a great thing to do. So banks made much more liberal terms for giving away money. And then in 2008, there was a crash, and because the whole system was way over leveraged, there was a crash. Didn't occur to the mortgage-backed securities people that that could happen and that all of these loans could be correlated in their behavior. They'd assume independence, whereas we were seeing a big bulk movement. And things crashed. And then we had a world financial crisis or a world economic crisis. Why? Because the real economy depends on credit. And credit went from being super loose before then to super tight after that. So this model isn't telling that whole story. But what it does tell is that there's a generic story that we should expect credit cycles to happen if we are not thinking carefully about what the long-term consequences, what the emergent phenomena can be. And let me emphasize that this happens because people were following a risk management strategy that looks prudent on the surface and was authorized by the Bank of International Settlements as Basel II was the right thing to do. But it turned out that it was, the problem is if everybody does it, then you get these feedback phenomena. And the reason you get this big crash is really because as leverage keeps going up and up and up, the system gets more and more unstable. And finally, leverage gets so high that some instability causes people to start selling. Once people start selling, prices go down. That causes people to have to sell even more to their creditors, and you get a big crash. So, yes.
You just said, in the previous slide, you said something about this bifurcation diagram that the stable point went immediately to a full amplitude cycle.
Yeah, not the stable point, the tracker went from being a fixed point to being, it basically jumps from a fixed point to a chaotic attractor that has a, significant amplitude. There probably is. Yeah, yeah. Okay, now I'm going to give you one more story like that, and I'm looking at the clock, so I don't want to spend too long. But this is another example of something similar. This is based on a very standard economic model that actually was originally due to an economist by the name of Robert Solow. And so his question was about growth, and he made a very simple model, again, a representative agent model. This time, even more heroically, there's just one agent is the whole global economy, one household. All right. So this representative household does two things. It has a business, so it makes a good that it consumes, and it makes a decision in every period of how much to consume and how much to save. And so he makes the assumption that the economy has what's called a Cobb-Douglas production function. So it's of the form some constant A times capital raised to the alpha power times labor raised to the 1 minus alpha power. And so this is equal to the amount produced. So it's usually called Y in economics for some reason. So if the savings of the household are invested in the household's firm at every period, and so that's this term K here, the household's also providing the labor. And so this term, the labor is constant, but the capital is changing. And notice it's raised to a power, so there's some nonlinearity here. And this term is just kept constant. And so what Solow showed is that, well, there's a sweet spot for the amount the household should save, depending on the way you adjust the parameters. The household wants, note something, if the household doesn't consume anything, then there's no demand for the good and nothing gets produced. So the household makes no profit. The economy is then stuck in a poverty trap. The household actually has to consume something. So it's this feedback loop that Keynes was the first one to realize is so essential in the economy. We produce things because people want things. People need to want things for us to produce things. Now, so what he showed is there's an optimal savings rate corresponding if you make all the things right. And okay, you can put some discounting functions so the household wants to not just do well now, but in the future. And so there's some optimal savings rate around 1/2. You save half of it and you consume half of it if you adjust the parameters right. Yeah.
Should that think of alpha like an interest rate?
No, alpha here is this is just stating the form of the production function. The interest rate, in fact, what you want to maximize is not just your consumption right now, but your consumption stream into the future. And that's where the interest rate comes in because there's a discounting rate that should be equal to the interest rate that you would use. Okay, very simple model. Now, Solow's conclusion was he then looked at different countries and looked at what their savings rates were, and he concluded that you could squeeze a little bit out of saving more efficiently and getting your production function right, but most of it has to be explained by this, which is technological progress, which I'll come back in the next part and say something about. Okay? But okay, so what we did, and we here is my collaborator Yuki Asano led it. But so we just changed the setup a little bit. Instead of having one household, we have a bunch of households, thousands of them, right? The households have a social network, right? And each household looks at the other households and periodically looks around to see who's consuming the most at that point in time. And they then get that person to tell them what their savings rate is. And then they adjust they take that savings rate, they make a small random modification of it. And then they start saving at that rate. And they go back to sleep, they don't pay attention for a while. And then at some point they wake up again and they look around and they say, who's consuming the most? And then they take their savings rate. So the households are all following some Poisson process for waking up. They don't all wake up at the same time with a characteristic time. I'll show you in a minute. So is the model clear? It's very simple. So it's just like the Solow model, except now you've got 4,000 households and they're collectively providing the labor. Oh, and I should say, and they're collectively getting the profits based on how much of the investment capital they get a wage from the labor, and then they get a return on the investment based on how much capital they supplied at each turn. Okay. So now what happens? We were pretty surprised. So this is social interaction time down here. And So if the social interaction time is really fast, I mean, the households are just waking up all the time, copying each other, the economy gets stuck in a poverty trap. There's the savings rate, right? So they all save very little. It's just handed out, they eat everything they have. And they're stuck. I need to show you a separate plot, but trust me, the production is very low in the economy. Because nobody saves anything, and that term K is always small. But now as we make the interaction time longer, we see the savings rate start to go up, and similarly, the production goes up, until we get up to the golden rule, which is that white line in the middle, which is where the rational agent would have told them to go, and under the parameters that we've set. And you can see that and okay, we're comparing some statistical mechanical theory, which is the dashed line, to what we actually measure. You can see our theory does pretty well. I'm not going to drag you through how the theory works, but if you're a statistical mechanics person, you recognize it. And we get up very close to the golden rule. So amazingly, with this really stupid algorithm, these agents are totally dumb. They're not like in the other case, the agent was being rational enough to figure out exactly where to adjust the savings rate. Here, they're just following two heuristics: imitate the best and trial and error. So they're making a little random variation. And you get up to the optimum. Now, then something weird happens. The system starts to oscillate, where some households are rich, some households are poor, and how some households can switch over generations from being rich to poor, and you get this cycle that looks a lot like a business cycle. So that's what's happening on the right. So here, I just show that. Now we're looking at we're still looking at the savings rate. Oh, but we're also looking at the production, Y. And so you can see something like a business cycle happening, where the whole economy's productivity is oscillating up and down, and where you have the emergence of extreme inequality, all from this very, very simple model. So nice example of emergence, also a nice example of how if you take a mainstream economics model, and in this case, I wouldn't say it's realism, but it's at least conceptual realism by heterogeneity, you can get very interesting things happening. And now, both of these are examples of how under bounded rationality, you can see systems that spontaneously move away from equilibrium. And so I've written about 4 or 5 papers over the course of 20 or 30 years on studying this in the context of games. In a normal form game, the way you have some number of players, imagine 2 to start with, and those players have some number of moves they can make, and depending on which moves the 2 players make, they get a payoff, which will vary depending on which move. So each possible combination of move has a table that you can put in the payoff matrix. And actually, you have a payoff matrix for player 1 and a payoff matrix for player 2. So we've actually exhaustively studied this under sensible, bounded, rational strategies. That is, maybe this is a bit of a long story, but we looked at, as it says here, 5 common learning methods. And these are methods that economists have used to study people in game theoretic context and have found they do not a bad job at explaining what people do. The typical thing is you look at the return you get from playing a given strategy, and if you tend to do well when you play that strategy, then you give it more weight. And I don't need to go into all of the details here. Let me just say that what we found is that learning doesn't converge to equilibrium if the game is complicated and competitive. In other words, if the game is if this condition is violated, then what happens is you settle into an equilibrium where the players just consistently play the same strategy over and over again. But if the game is both complicated and competitive, complicated means the payoff matrix is big. Competitive means that if player 1 wins, player 2 tends to lose, and vice versa. Then the game will not settle into a fixed point equilibrium, it'll tend to oscillate. This requires bounded rationality. Now, the analogy I make, and a few of you who were at my talk, my cocktails talk, maybe I should say a little bit about this slide. What do I mean by bounded rationality? I mean, the players can't figure everything out. They're incapable of knowing everything. They have some, hopefully not too stupid way of doing stuff. They're doing the best they can. It's an idea due to Herb Simon. And traditional economics enters through what I call a rationality gate. They assume perfect rationality. Physicists like me tend to go through the zero intelligence gate. I have a paper I'm very proud of where I showed that if you assume investors just place orders at random prices, then, and if I know the order flows, I can predict the bid-ask spread, that is the distance between the best selling and buying price, pretty well. So we had a P&S showing that. But so the reality is more complicated and we need to move in the middle. Now, the point I'm trying to make here is that having bounded rationality that is not being perfectly rational is essential in both these models I have. And the example I'll use to illustrate it is a man balancing a pole. This pole should work better than the other one I had. So suppose I'm balancing a pole. Now I want you to think about the economy is the pole. And if the pole is perfectly vertical, the economy is roaring along. We're at full capacity. The output gap is zero. If the pole starts to tip over, then the economy isn't doing as well. There are people who are unemployed who could have been put to work if we could get it to work right? Now, we look at real economies, that output gap is changing all the time. Now, why does it change? If you're a mainstream economist, you would say the reason it changes is because of the shocks. The shocks hit the pole tilts, but then the pole balancer is now all of the decision makers in the economy, the people who run businesses, the central bank, everybody else. They all make their decisions and they all do it perfectly, and the pole goes back, it would go back to being perfectly vertical in an optimal path, except that some shock always hits before that happens and knocks it out. So there's this ideal pole balancer. But now when I do it, is that what's happening? I don't think so. What's happening is that there's no particular shocks. I mean, if I were on the deck of a ship during a hurricane, it'd be different. But there are no shocks hitting. What's happening is I'm not a very good pole balancer. And so when the pole starts to tip, I move my hand, but I overshoot, I undershoot, and so the pole keeps wobbling around. That's essentially what was happening in both the models I just showed you. All right, now I'm going to change the channel and get back to what something a little more fun, maybe. Back to this question of the economy as an emergent phenomenon. So I was talking about a weak sense of the dynamics of the economy as an emergent phenomenon. But the whole economy is an emergent phenomenon. Just trace the course of civilization. And already this fellow, Imam al-Ghazali, in circa 1100, made the statement that in fact, we're all specialists, we're all doing different things, and we're all combining the specialized labor to produce goods by trading with each other. And as he says, one will find that perhaps a single loaf of bread takes its final shape with the help of perhaps more than 1,000 workers. So somehow we go from being, simple hunter-gatherers who, even there's probably already some specialization going on within the groups, to much, much larger groups where the labor becomes more and more specialized through time, and we've gotten richer and richer. Now, I'm going to then trace you a bit through the growth of population, because I'm going to argue that population provides a measure of how emergent the economy is. Because, well, basically, in prehistoric society, we have relatively simple technologies. The carrying capacity for human beings on the earth was small. And as we have developed technology and the economy in general, we've increased the carrying capacity of the planet by a large factor. How much? So I'm just quoting here Malthus. Malthus is very famous for, basically pointing out that if you get overpopulated, people will die, and that population when unchecked increases in a geometrical ratio, subsistence increases only in an arithmetical ratio, overpopulated world of misery and vice. He was a Presbyterian minister and was very concerned about prostitution. And that's really what had him upset when he said this. But notice, he's responding to several other essays, including the Marquis de Condorcet. So the Marquis de Condorcet is one of my heroes, wrote the sketch. What? Yes. Subsistence is getting along, enough to live. It's like your subsistence, a subsistence wage would be enough to keep you alive, but not more. Okay, thank you. Condorcet is one of my heroes, wrote this sketch for a historical picture of the progress of the human mind while he was hiding during the French Revolution, because he knew they were going to kill him. So he wrote this amazing piece, which was devoted to his daughters. And he predicted in this piece all kinds of things that have happened. And colonialism, the spread of democracy, universal education, equality of the sexes, welfare and social security, merit. He didn't use these words, but if you read the essay, you see that he's essentially talking about that. Merit-based venture capital. I mean, we take it for granted, but back in those days, you couldn't just say, here, I've got an idea, go to some people, have them give you money. At least there was no real infrastructure for doing that. Increase in the human lifespan, acceleration of knowledge and well-being through feedback between education, science, and technology. And he did say that we will reach a day when the Earth will eventually become overpopulated. But he was aware that because of the progress of technology, the population of the Earth had been going up. And now here's a paper, actually early, these are Heinz Forster is one of the people that was involved in the cybernetics movement. And they wrote, this paper was published on November 4th, 1960. He actually wanted to publish originally on April the 1st, because it's sort of a joke. But it's not. And in fact, it was about, he said there was a finite time singularity where the human population would approach infinity. And if you read the paper, he says, people will die not by starvation, but by being smashed together. He's joking. But he was responding to the fact that they collected data on the world population. And if you plotted it, up to 2000 from the time of Roman times, it looked like that. And so on linear scale. So now you can plot it on an exponential, on logarithmic scale. It still has a substantial amount of upward curvature. So they did a function to it, and they concluded that it was a finite time singularity. So this is showing you how these things work. There would be arithmetic growth, geometric growth, and double geometric, that is, well, what I'll show you in a minute. And now, since the people have kind of made a justification of this, so why does our population grow? Our population grows because we get better technologies for producing food, basically. Health makes a bit of a difference. We can extend our lifespans, but when you go from a 30-year lifespan to a 80-year lifespan, that's an increase of a factor of 2 or 3. That's not the main part of the story. The main part of the story is just how much food can we produce? And so now, but if you assume the rate of population, there's some factor R of T, which is the rate at which the population is increasing. That's the reproductive rate. Now, let's suppose we also have technology changing so that as the population gets bigger, we have more inventors. Maybe we also have things like better communication. So we have a bigger infrastructure for producing technology, so that increases. And so now we have a feedback loop between the population and the rate at which technology is improving. And when you just solve these equations, you get something like this, that the population has a finite time singularity, which Von Forster estimated was in around 2026, excuse me. So this was written in 1960. Now, so it is telling us what an essential role population plays. Now, back to my question about, let me just also show that, no, this is what happens when you look at world population, graphing it with this, assuming this function. So you pick some TC, and then you graph it, and you get a straight line, so you can see that it works better. It's not perfect, but of course, you also have to keep in mind that these data points are pretty sketchy as you go backwards in time. And let me also say that this is debated. Others will say the whole thing was due to the Industrial Revolution. We were basically going along, things weren't changing very fast. And then the Industrial Revolution happened. I favor this viewpoint because when you read the Industrial Revolution, technology has been improving steadily even before the Industrial Revolution. Though the Industrial Revolution is clearly very important. Now, of course, why is that not happening? It's because as women get educated, they have less children. So we're scheduled to instead land around 10 or 11 billion. By the way, there's a great book on estimates of where will the world population end up through history. The person who was the best at this was Van Leeuwenhoek, the inventor of the microscope. How did he estimate the global population? He said, well, Holland's pretty well populated. He looked at the population density in Holland. He said, let's assume that happens for the whole world. And he got about 10 or 11 billion. So, so anyway, pretty good. Same thing happens for economics, although I'm even more skeptical about estimates of GDP. I don't know what they mean much, but similar kind of thing happens if you think about that. Now, how are we going to quantify, how am I going to use this to quantify the degree of emergence? Well, I would argue that the population then is measuring how big a role, what does the economy manage to do? It's managed to enormously amplify our layers. If we suddenly all turned into Robinson Crusoes, so you weren't allowed to get anything from anybody else, you had to collect your own food by yourself, you know, almost all of us would die, not just because we don't know how to do it, because the planet can't support that. Planet, you know, if you go back to say 10,000 BC, we weren't, Malthus's idea happens at a very fast time scale. If you look, just plug in the numbers, you can see that you quickly get to the asymptotic population with a fixed carrying capacity. In a matter of, you know, 10 generations, you're there. But, so if, you know, the estimates of the population in 10,000 BC were between 1 and 10 million. And so it's now going to be the order of 10 billion. So the amplification factor is between 1,000 and 10,000. So the economy is doing a lot for us. It's worth keeping that in mind. And you see how fragile it is when you can elect an idiot to the White House and he starts just playing with the control knobs at random. And, you know, if he hadn't backed off on the tariffs, the global economy would have really crashed hard. Just a reflection on technological progress, which is, after all, what's driving this. I always have another lecture I give on technological progress. This is my favorite picture of a man on skis from the Stone Age. He's got his cool little, you know, pole that he's using and pretty big skis. But, you know, we've been messing with technology for a long time. So here's on one hand a voice terrible influence of this race, which serves neither God nor king, given over to the mundane sciences, to base mechanical professions, pernicious breed. What will you not attempt, left to your own devices, abandoned without restraint to that fatal spirit of knowledge, of invention, of progress? Versus Condorcet, who, by the way, as I said, he devoted his essay to his wife, to his daughters, and he advised them, learn a trade. Don't depend on your husband. Make sure you can support yourself so you can be independent. So there were some far thinkers back then. Now, so some forecasts. I'll end the lecture with that. 21st century, we will, excuse me. I think the human population will finally stop growing for the first time in history. We're going to wreak havoc with the Earth's ecosystem. We already have, but it's going to get, unfortunately, I think, quite a lot worse. I think eventually it'll spring back, but we have to learn the lesson the hard way. We're going to understand basic principles of biology. I mean, we still don't really understand fully how things work. So we'll be able to genetic engineer human beings. We're already doing that to some extent to prevent diseases, but I think we're going to start doing it in a much more dramatic way. If anybody's seen the movie Gattaca, completely plausible to do that. And computer powers will exceed the human brain. In fact, we're at the point Hans Moravec in 1990, and I was around back then, and we were debating these forecasts back then, extrapolated Moore's law, made a back of the envelope calculation of how many synapses we have in the brain, how many transistors we would have if Moore's law kept on going, and the crossover points also around 2025. And so he said, I think we're going to finally get AI around 2025. Pretty good forecast. We don't have real AI yet, though I think people overestimate how much are in large language models. I strongly recommend the book by Max Bennett called A Brief History of Intelligence, which traces the genetic evolution of the brain, of the human brain, and from corals to the human brain, and the key breakthroughs that happened. And you can see that he actually talks about it in parallel with AI, and we've sort of gotten up to nematode worms in terms of the conceptual level. But I think we're going to have artificial intelligence. Oh, and I can't help but throw in a slide about, predictions like this are usually bad, but Jules Verne, most people don't know, he has a second novel that called Paris in the 20th Century. And he wrote this novel and he went to his publisher, and the publisher said, no, this novel's too depressing. People aren't going to like it. Nobody's going to believe it anyway. And he went back to writing novels like Around the World in 80 Days. And, but, what did he predict in 1860? He predicted the heroes of long hair, disaffected dropout, bright electric lighting, gigantic hotels, electric trains, internal combustion cars, fax machines, copiers, calculators, starving homeless people, young people who feel disillusioned and bored by their tedious jobs. So sometimes these predictions work out to be true. But okay, that's just sort of veering off into fun. So anyway, with that, I'll end the talk. Thanks.
So thank you very much for the talk. Is there any questions?
Yes?
One question that actually the first part of your talk, where you showed that you have spikes in leverage, and they coincided with two, whereas in real life it didn't.
Yeah.
And I wonder that phase difference should tell you something about what is missing from that model.
Yeah, yeah. Yeah.
What is missing, the heterogeneity, heterogeneity in the bias, in the profiles, and heterogeneity in fundamentalists.
That's a very good question, and the honest answer is, I don't know. It would be a good thing to figure out. I mean, it would be, I think one could develop this model, make it heterogeneous, and I do think that would provide some more richness. Whether it would solve that problem, I'm not sure. I don't know. Because we got close, but not quite. But I think that's an important clue about something missing. Now, there could also be a data artifact. I mean, it's true that these things, but I don't know. I don't know. Other questions?
So you have this phase diagram.
Yeah. Yeah.
And if I understand correctly, we could put ourselves somewhere there. Like, what is the values that the banks actually set for this risk target?
Yeah. 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 So this goes, let me, good question too. So this is a phase diagram, you know. Now, it's a little hard to say because the plot I showed is for broker dealers. So it's a very specific kind of investor that Lehman Brothers was one of. And they're not even, they even aren't all using the same leverage. Some of them are more aggressive than others. And also it's tricky, the quantitative investment firm that I ran during the 90s, called Prediction Company, we also use leverage. We use leverage at about 7 to 1. Why? Because that was what we legally were allowed to do. Now, but for our type of investment, there are other investors who use much higher leverage, but some investments are intrinsically pretty, the risk is quite low, and so it can even make some sense to use these really high kinds of leverage. So to really understand this, you have to look at, you have the heterogeneous leverage, you have heterogeneous risk in the investments, and you really have to parse all that out properly to get this right. But what do I think happened? We were in the stable region, we went up into the unstable region with leverage cycles, and then we came back out of it again. And
I think we're always in the leverage cycle part.
we're not always in, I don't think we're always in there because there is a parameter being turned in the background of, in the US, it's by law. Right after the 2008 crisis happened, there were things called the Volcker rule, actually directly affected my company because, well, it got sold to United Bank of Switzerland. The Volcker rule came in, which said you can't have the same institution doing business with the public and making proprietary investments. So they told everybody at Prediction Company, we're all in Santa Fe, New Mexico. I'd already left by then, but you guys need to move to London. They said, forget it. They got sold. Anyway, the Volcker rule is a smart idea. Why? Because if you have the same institution doing both, it's a contagion mechanism. Prediction Company also felt that because they had all these other investments. Prediction Company was doing great. When they lost a lot of money from their mortgage-backed securities, they stopped paying bonuses to the people at Prediction Company who were making them, you know, $35 or $50 million a year. And everybody left and went, the good people left and went elsewhere. So, okay, that's too long an answer. But the point being that, yes, the regulatory space is changing all the time, and that determines where you're going to sit in this diagram. And there's a tendency, as Nancy pointed out, to get greedy and wander up into the unstable part and learn the lesson the hard way. We're probably going to do that again in the United States. So all the regulations are being pulled out. Yeah. You are messing. All right. You go first.
Thank you for the talk. You argued that how to quantify emergence can be by the change of carrying capacity, but all the works you showed carrying capacity, I guess, was defined by wealth. So is there any, I don't know, discussion around this on ecology and other places where emergence is also seen about?
Yeah, well, interesting, not that I know of. Of course, the same thing's happening in real ecologies because of niche construction. You know, animals or plants are actively constructing niches, which then allows their carrying capacity to go up. But I think we're probably the only example where it's gone up by a factor of 10 to the 3 or 4. It's pretty dramatic. Yeah. Well,
would you mind going back? And first of all, thanks for the really interesting talk. Would you mind going back to the slide with predictions?
sure. Oh, yeah, sure. the fun slide. Okay,
If I remember correctly, most of those predictions concern technological development.
they do.
I'm wondering, how about ethical, moral, cultural developments?
Ah.
And how should, what kind of ethics do we need to keep up with this kind of technological advance with the fact of emergence and the complexification
Yeah.
of our society?
Yeah.
And what do you think, how do will we face this problem?
Yeah, well, I think we'll probably continue to face this problem the way we usually have. We just kind of blindly stumble along and stuff happens. I mean, I did, for those of you who were at my Science and Cocktails talk, I do paint a vision of how we could become a more conscious civilization by actually modeling ourselves. But we'll see how good we are at that. You know, we have some ability to do that now. But ethics, I think, okay, I have a bit of a radical view on this. What are ethics, right? There are things that evolve. Every society has different ethics because, you know, there are rules that you give people so that we can cooperate with each other in some effective way. And societies that evolve a certain moral code that may be effective. What does effective mean? That society propagates. That system of ethics goes forward because those people in the past, unfortunately, they conquered some other people usually, or maybe they just didn't kill themselves. So I think of ethics as something that are evolving and that we use as a civilization to, to make our collective behavior more effective. So I think we will see a big evolution of ethics once we have the crash. Once we really crash the Earth's ecosystem, ethics about the ecosystem will change. Now, but we always have the problem, as everybody knows from the prisoner's dilemma, of the defectors. There's always some evolutionary pressure to have defectors. And so you have to have a system that is stable with respect to those defectors. You know, and back in the day when we lived in tribes, we had 130 people in a tribe, the Dunbar number, more or less, putting the cap on how many people we interacted with. It was pretty easy to know everybody. And, you know, I want that person as the leader. If that person doesn't do a good job, you make somebody else the leader. And it was, social regulation was much easier to do well in that kind of unit. With 8 billion people on the planet, we're failing miserably at this all the time. We have no effective world government, and at this point, you know, a large fraction of authoritarians are running many important governments. So I think we'll see ethics continue to evolve. I guess I wrote this is, by the way, a 15-year-old forecast, because I was grabbing slides from ancient times. I actually wrote a paper in 1990 called Artificial Life Becoming Evolution, where I really talk about this more seriously, because I think we will be the first species to actually create our children. We will change the children and we will begin evolving. I mean, Ray Kurzweil says some version of this, so I think he gets pretty wacky in a hurry. But I think we'll be the first to do that. And I think, so we need to, but ethics will be a very important thing in how we make that transition. So, yes? Yes. Yeah. Well, yeah, I mean, I think we're going to probably, I mean, I'm going to be giving a lecture at the Institute for Advanced Studies tomorrow at a climate conference. So that's another thing I work on. And I think that, I think the good news is that solar energy is going to become by far the cheapest source of energy. And so the energy system will convert over, will become green, and will stop making emissions from the energy system within about 25 years. we have probabilistic predictions for that. The bad news is that lands us at around 2 degrees of warming, which is already pretty substantial. And the worry is we could lose Greenland ice sheet. There's a feedback mechanism. If the mountains get below 3,000 feet and they're just all made of ice anyway, then they go all the way down. So we get 2 meters just from Greenland. We get another 3 meters or 4 meters from the Antarctic ice sheets. So we're going to have a mess. Now, on the other hand, is it going to kill us all? I don't think so. One of the things that gives me a little bit of solace, I'll ask you guys a question. What is the hottest temperature the Earth has had during times where, living things are on the Earth? Does anybody know the answer? How much hotter than now?
Can you?
Yeah, question is, how much, if you look at the Earth's history, the Earth has gotten hotter and colder. So what was the maximum temperature the Earth had? And extra points if you can say when. Pardon?
100.
100 degrees more?
Yeah.
No, Celsius? I mean, no, that's not hot. No, we would be boiling at that, right? 100 degrees would be boiling.
The whole history of life with humans.
No, not with humans, with life in general.
I thought about the whole history of life.
Sorry, I couldn't hear.
I thought about the whole history of life.
Yeah, whole history of life. I mean, the really early, let's maybe do it since the Cambridge explosion.
Well, I know the name of the event, but not necessarily how old it was. This is Paleocene Eocene thermal maximum.
All right, this guy knows his stuff. But yeah, so it's around, as I recall, around 50 million years ago, and the answer is 14 degrees Celsius hotter. So that's a lot hotter, right? Now, and the Earth, interestingly, and then there were forests on Antarctica. The whole system was, the weather was very different, but life thrived on the Earth at that point. Now, there is some, if we go up to 100, forget it, right? It's gone. So there is some temperature up there that we just can't go above without killing everything. So back to your question, I think we're going to survive, but we're going to have to move all the cities, or maybe the Dutch, I'm learning about the lunch. You guys think it's okay to live, 10 meters under sea level. Maybe you'll just make dikes around the whole world and Holland will become, leading technology provider. Polar bears forget it, they're all gone. So it's bad, but the Earth has changed a lot in the past and restoration is often possible. A lot of people at Oxford are talking about what it takes to pump carbon out of the atmosphere and bring the temperature back to where we are. And with super cheap energy, super cheap clean energy, we can do that if we want to. But we'll still have persistent, for hundreds of years, persistent effects because things don't reverse easily, if they reverse at all. You had a question?
All these examples many of the examples are pointing at some form of economic growth or technological innovation, and the production function in this case is very simplistic with labor and capital. But I imagine there are many other factors, or if you want an economic spending, binding constraints or chemistry spending, rate limiting steps or something. And I just wonder, what do you think those are, and which ones are fully understood?
Rate limiting steps, let me make sure I understand. Rate limiting steps in the process of growth going forward? Yeah. Well, technological improvement, technologies pile on top of other technologies. So that's the remarkable thing that's allowed us to have this, factor of 1,000 or 10,000 growth, this technology, which is cumulative and which we can communicate to each other and remember and everything. And that, generally, you don't just have something, radically change everything all at once. So I think we'll continue to see, on the other hand, I think it is growing faster and faster, and fast enough that it's causing us a lot of problems right now because we haven't really understood how to govern our physical technologies with social media. But rate limiting step, I'm not totally sure I know what you mean. Maybe give me an example of what you're thinking about.
Yeah, so. And provided one just now, so the idea like, we produce the technological advancement, but like the regulation effort is not on pace with that.
Yeah.
We cannot fully reap the benefits of it.
Yeah,
Further building on top of that is kind of limited by maybe an institutional or societal backlash, or I don't know. What
yeah, well, those things are, that's part of the regulation system, but it's gotten out of whack. I mean, if you go back and you read history, this has been a problem consistently. Even railroads, for example, they were controversial. People didn't, there was a question of the right of eminent domain. Can we just plow through somebody's land, force them to sell it or not? There was a lot of graft. You know, it was the downfall of Native Americans in North America. So, yeah. So I think it goes back to the question about ethics and how are we going to keep things regulated? And I think it's a problem because things are moving so fast. We're not very well set up to deal with that. And I am worried that's one of the big problems. Yes?
So we have one that forecast for the future, we have also the past forecast, but most of the talk were about the crisis 2009.
Yeah.
And modeling things around it. What happens if we take your model and we take our data up to now and we move it forward? Where is the next slide?
Yeah, I don't know. It kind of goes back to the question that Frank had of because it's hard, it's some work to even measure where the leverage is now, and I don't have a graduate student who's doing that. So but at macrocosm, I hope within a few years we will be able to we'll just be tracking that stuff, gathering the data so that we know. I mean, by the way, in the 2008 crisis, I was not totally shocked because a guy who was on the board of the Santa Fe Institute about 2005 started sending me emails. Do you see the leverage these people are using? Do you see this? He's really concerned that some shit was going to hit the fan, and he was right on that. That's exactly what the problem was. But it's hard to track because the sources are scattered all over the place. A lot of the data is confidential and so forth.
Do you think if you would start doing that, tracking leverage and using it to predict this, that something like Goodhart's law would come into effect and it would immediately cease to be a good measure?
No. So I know Charles Goodhart. I even have authored a paper with him. He's a fantastic guy. He grew up as a kid very near where I now live. But there are circumstances where Goodhart's law for everybody says as soon as you have some regulatory mechanism, people will figure out how to game it and it won't work anymore. Or am I? Yeah. So sometimes that's true and sometimes it's not true. And I think that, it depends. Unless there's some way people can get leverage without having it measured so that they're not covered by the law, okay, then it will be true. But I think it's pretty fundamental, higher leverage makes the economy more unstable. And one of the things I would do if I were a regulator, I would make the leverage for purely financial investments quite low, but allow much higher leverage for real investments. Because the real investments are what actually produces stuff. The highly leveraged, purely financial investments are just people playing in a casino to make money. And I think have very little actual value. But that's a controversial opinion. Yeah.
The simulation showed for the cycles,
Yeah.
you're all for Basel 2, but what happens if you add Basel 3 to your system? Does the whole thing stabilize again? Or
Yeah. Good question. So we did think about that. It's funny, I had a whole cadre of Dutch graduate students who worked on this topic. Christoph Eimans, who did the other model, was German, but I had 3 different Dutch graduate students that worked on this. They're all gone now, so I'm not updating things as fast. But we did look at, in the model I showed you, in the latter part of the paper that I didn't talk about, we looked at how do we make the system more stable. So the main way we saw to make things more stable is to make sure things don't happen too suddenly, let people adjust gradually, let them pay back their loans to their creditors gradually, and then that makes everything much more stable. We also investigated rules that were much more like Basel III, and they help, but the problem doesn't go away with Basel III. You still have to keep greed in check so that people don't leverage too much. And that's just seems to be a law. You can do it, you know, you can do it better or worse, and you can, you know, there's like a factor of 2 of play, but between a really stupid leverage management policy and a really good one. But there's a hard ceiling up there. Thank you.